Okay, so another thing that I want to do in terms of undecidable problems about context-free languages is I want to talk about the intersect CF problem. Okay, so I've already written some of this stuff down. So the intersect CF problem is a decision problem about a pair of context-free languages, which asks whether they have some element in common, right? So whether the intersection of L1 and L2, which are both context-free languages, is not empty. Okay, and it's a question about context-free languages, but remember, how can we actually talk concretely about these context-free languages if we wanted to actually design some type of algorithm that worked with these languages? We would need some finite representation of them. And to do that, well, in this case, we're going to assume that we have context-free grammars G1 and G2, which accept, or pardon me, which generate those languages. If you instead wanted to represent the languages with PDAs, then that's okay, because if you have PDAs which accept languages, you can convert those to context-free grammars. So assuming that we have CFGs doesn't cause any loss of generality. Okay. And so the question is the intersection non-empty? And it turns out that we can show that this is undecidable via a mapping reduction. And this mapping reduction is, in this case, from the vanilla halting problem to this intersect CF problem. Okay, and remember why we're doing this, because, suppose I have some instance of the halting problem. I feed this to the instance modifier. I get G1 and G2, a pair of context-free grammars. And I feed that into the intersect CF solver. If it says yes, right, meaning that the intersection is not empty, then what I should do through this mapping reduction, so really through this instance modification, is I should be able to show that this maps back to a yes answer to the halting problem, to the instance of the halting problem, meaning that M halts on X, right? So if this is true, if the intersection is not empty, then M should halt on X. If it is empty, right, if it is empty, then M should not halt on X. Okay, so how can I possibly do this? Well, the intuition is I'm going to want to create, so I'm going to design G1 and G2 such that its intersection is a very special language. The intersection is going to be another valcomps, but it's going to be valcomps 2. Okay, valcomps 2 of MX. Now, what is valcomps 2? What is valcomps 2? So it's very similar to the vanilla valcomps, right? It's very similar to the vanilla valcomps. Suppose I have some string over the alphabet delta star, and that string is a valid computation history string. Right. Of M run on X. M run on X. Okay. Then what valcomps 2 contains is not quite alpha, just slightly modified. So how do I modify this alpha? Well, at every even position, I have alpha 0. At every even position, I have the same alpha as in the original valid computation history. So, alpha 2, alpha 4 is unchanged. But at the odd positions, right, I have the alpha i's reversed. So in other words, here, alpha 1 is reversed, alpha 3 is reversed, and so on. And so here, if n is even, then there's no reverse. If n is odd, so, if n is even, then it should just be alpha n. If n is odd, then it should be alpha n reverse. Okay, so, we're taking the valid computation history, which is just a string of instantaneous configurations, and we're reversing the odd position instantaneous configurations. Okay, so why are we doing this? Well, because it turns out that this language itself is not context free. Okay, it's impossible to generate a context free language. Come on, it's impossible to create a context free grammar which generates this language. There, that's better. But it is possible to create two context-free grammars, which, when you intersect their corresponding generated languages, gives you valcomps 2. Okay, so what is that? Well, consider instead of G1 and G2 for now, the PDAs, two PDAs. So PDA P1 and the PDA P2. Okay, and so what the PDA P1 does, is when it reads this string, so let me just copy this string. When the PDA P1 reads this string, what it's going to do is it's going to check that the consecutive even to odd alpha I plus ones are consistent. Okay, so this alpha 0 does indeed follow from the next one instantaneous configuration to this alpha 1 reverse. Or really it should have been, that alpha 1 reverse does follow from alpha 0. Okay, and then that alpha 3 reverse does follow from alpha 2, and alpha 5 reverse follows from alpha 4, and so on. Right, and I can do this because I've reversed the string. Right, I've reversed the string, so I can push all of the string alpha 0 onto the stack. Right, because alpha 0, that's some string u, then you have the 3-letter window, let's say a, q0b, and then v, and then I have alpha 1 reverse, which is in this case, let's say that alpha 1 originally is u a b q1 v, because in the Turing machine M, when you're at say q0 and you're reading v, you move the pointer to the right and you don't overwrite the b. So this is the correct next instantaneous configuration based on M. Then alpha 1 reversed, well, that would be reversing this entire string. And so we didn't show this formally in class, but if you have some string xy and you reverse it, well, that's y reverse x reverse. And so what we have here is v reverse q1 ba u reverse. And so if you push all of this onto the stack, and then you match it by popping and verifying that it's equal to this string, then you'll be able to check whether or not alpha 1 reverse is actually the corresponding next instantaneous configuration of alpha 0, reversing it, of course. And so the one thing, of course, is that this 3-letter window is not actually going to match with this 3-letter window. And so what you need to do additionally in your PDA is you have to do the same kind of memorization or hard coding that we saw in the AllCF mapping reduction, where you first push onto your stack, right? So you first push onto your stack U, then you guess that you're at the 3-letter window with the state Q0, and you go through that path, you go through that branch that has a Q0B, then you keep pushing the V, right? You keep pushing the V. So then on your stack, at this point, you have V and then U, but you have the top, you have the sort of last string of V at the top. And so now you can pop here and match that with V reverse. And then you can at some point guess that you're at the 3-letter window and check that this matches, that in this case, it's only one possible branch that should be able to verify. It's the corresponding correct branch, but reversed, right? Right. So what I mean is, because everything is finite, and for a 3-letter window, there's a single correct corresponding 3-letter window, then you hard code this, and instead of just hard coding this, you hard code this reversed, right? So then you match this path with this path, and then you've popped the V already. So then the only thing you need to do is you need to pop this U and match it with this U reverse. Okay, and so that's how you could recognize not languages, not strings in this language valcoms2, but strings almost in valcoms2, strings where there's this correspondence between even and odd positions, right? So the only thing you're not checking is the odd to even positions, right? Because these could not match. It's possible. And so to do that, well, that's why we need a second PDA, right? So in the second PDA, Well, let's just write his. So in the first PDA, you match alpha 0 with alpha 1 reverse, then alpha 2 with alpha 3 reverse, and so on. And so in the PDAP, what you're going to do is you're going to match alpha 1 reverse with alpha 2 using the same logic. Okay, so for the PDA2, you're going to match alpha 1 reverse with alpha 2. And then, let's see, alpha 3 reverse with alpha 4, and so on, right? And so on. And the idea is if you match the even with the odd positions, so this part of the string, and you also match, so let's see if I can do this. Let me use some colors. So if you match these guys together, and then you also match these guys together, then there's a transitivity argument you can make, right? So if this matches with this via P1, and then this matches with this via P2, then if you have a string which matches, which is accepted by both P1 and P2, then that means that it's originally in valcomps2, right? Because valcomps2, it has a proper valid computation history, but the odd positions are reversed, right? And so using this intersection allows you to verify this. So then if you take the intersection, right, if you take the intersection of converting, let's say, P1 to the grammar G1 and P2 to the grammar G2, then you'll get that the language generated by G1, sorry, intersect the language generated by G2. Well, that's exactly equal to valcomps2 of MX, right? Because remember, for a string to be in valcomps2, it has to be this alpha 0 to alpha n, where you're reversing the odd positions, and the alpha I and the alpha I plus 1 correspond via this next one instantaneous configuration of the Turing machine M, right? And so if you have a string in here, well, that means that, you know, the alpha i's correspond at even positions and also at odd positions, okay? And so that's just when the string is both in here and in here. Right. So we have this equality, and now remember what we're checking whether when we give G1 and G2 to the intersect CF solver, whether the intersection is not empty, right? But if the intersection of valcomps2 is not empty, it's the same conclusion as if if valcomps is empty, or if valcomps2 is not empty, then it's the same conclusion as valcomps being not empty, because, you know, it's the same string, right? It's the same string, except that we just did a few manipulations here. But that's not going to affect whether or not it's in valcomps based on M running on X, right? Because if M halts on X, then it doesn't matter how we're manipulating the valid computation history, it's going to be here, right? And so if this is not empty, then that must imply that M halts on X. So we have a yes instance. Otherwise, if it's empty, right? So if this is empty, if this is empty, and if you didn't really follow the argument I just made, well, you could probably convince yourself that that means that the vanilla valcomps is also empty. And if the vanilla valcomps is empty, well, that means that M loops on X. And so that's a no instance, right? So here I have a yes, and here I have a yes, and here I have a no, and here I have a no. So I do indeed have that the halting problem mapping reduces to the intersect CF problem. And so because the halting problem is undecidable, so is intersect CF. Now let's see, is intersect CF CE or co-CE? Let's think about it. So if the answer to the intersect CF problem is yes, then that means that the intersection is not empty. So then you can check that, right? You can check that by saying, well, run a for loop on sigma star, and then run the CYKS algorithm on G1 and W and on G2 and W. And the CYKS algorithm halts in finite time all the time because the is-in problem is decidable. And so eventually, if you know that the intersection is not empty, there's going to be a string which is generated by both grammars, at which point you can accept. Okay, so that shows that it's CE. So it's undecidable, but CE. And so it cannot be co-CE because by Post's theorem, that would mean that it would be decided. Great, excellent. And so that shows that the intersect CF problem is undecidable, but CE.